Right, welcome back everybody. Today we're doing our third objective, transformations. Let's get going with that here. So when I say transformation, we're talking about a change in the position, shape, or size of a figure. Okay, I'm going to say transformations are something that are happening in your world all the time these days. Okay, if you think in terms of a video game or a computer animation, basically what's happening there is they have a geometric figure, okay, whether that's your sprite in the game or the character in a movie or something like that, and then it's just continually changing its position, shape, size to actually make that motion, make that movement happen. Okay, so something going around all around you. Okay, important topic. We're just going to do some very basic transformations today. We got 3 of them for you. And the first one is probably the most basic of the basic, a translation. I'm going to say a translation is a transformation that maps all points of a figure the same distance in the same direction. Okay, so the result of a translation is just taking that figure and sliding it, okay, translating it across our screen here. So let's make some translations happen. Problem 1 says find the image of the vertices of each triangle after the given translation. Okay, so I have a triangle. Now, transformation vocab in general, I'm going to say that I'm starting with the pre-image, and I want to come up with the image, the new image, after my transformation. Okay, and the way we'll describe translation rules is like this. We'll say that a set of coordinates, x, y, gets mapped to x minus 2, y minus 5. That means take each of the original x coordinates, x and y coordinates, and subtract 2 from the x and 5 from the y. All right, so right now we're looking at, let's start off with point A. Point A is currently at -1, 3. So I'll take A at -1, 3. And I'm going to transform that by this rule. I'm going to say I'm transforming it into A prime. That'll usually be the notation we use. We go from the kind of capital letter to the capital letter point with the apostrophe there, okay, to show it's the image. And we'll take that x coordinate -1 and subtract 2 from it. So -1 minus 2. And then the y coordinate of 3, we're going to subtract 5. And just doing that math, -1 minus 2 is a -3. And 3 minus 5 would be a -2. All right, so after this translation rule, my A is going to move from the -1, 3 to a -3, -2. All right, so like I said, that's one way to think about making our translation happen. Kind of think of them arithmetically, okay, with the arithmetic. Now the other way, and probably the more convenient way with our graphs, is to think of things more visually. We can think about what is this rule here doing to each point when I subtract 2 from the x and 5 from the y. Well, my x direction is my left and right direction. Y direction is up and down. So if I'm subtracting 2 from the x's, that's just going to move all my points left 2. And subtracting 5 from the y is going to move all my points down 5. So if I go to point A here and follow that rule we just came up with, left 2, down 1, 2, 3, 4, 5, we get to the same spot. It's probably easier to do that graphically if I take B, same thing, left 2, down 1, 2, 3, 4, 5. I can find my B prime. And C, same idea, left 2, down 1, 2, 3, 4, 5. Okay, probably a quicker and, like we said, more visual way to make those translations happen. All right, so I'd say this new triangle, A prime, B prime, C prime, is my translation image. And when a translation happens, you should end up with 2 congruent figures. Okay, these 2 triangles should have the same angles, should have the same side lengths. Okay, so if you actually distorted that triangle with a translation, you know you did something wrong. Now in problem 2, we're going to work on describing a translation with rules. Okay, so it says write a rule that describes each translation. For part A, we want to go from PQRS to P prime, Q prime, R prime, S prime. So in other words, the figure on the left to the figure on the right. So essentially here we're doing the opposite of what we just did in the last problem. Last problem we gave you the rule, you came up with a translation. Here we're giving you the translation, you want to come up with a rule. Alright, so the way we write translation rules is we'll say that the point xy is going to get translated to x with something happening and y with something happening. Now let's figure out what those somethings are. Okay, I need to pick a point to start off with. We can pick any point on the pre-image. Let's go with the point P. And it looks like to get from P to its corresponding point P prime, we've got to go right 1, 2, 3, 4, 5, 6, 7. Sorry, 8. All right, 8. It's a little hard to count and draw at the same time. So that means my x piece, the left and right piece, is going to be x plus 8. All my x coordinates are going to increase by 8. And then from there, we'll go down 1, 2. Okay, y is my up and down direction. And to go down, we'll just go minus 2. Okay, there's my rule that describes how to get from the pre-image to the image. Now, I could have picked any other set of points. Let's see here, if I went from R to R prime, it's going to be right 1, 2, 3, 4, 5, 6, 7, 8 as well. Okay, and down 2 as well. Okay, so it doesn't matter which point I pick to start off with, as long as I get it to its corresponding point on the image. Alright, so that's how to write translation rules. Once again, take a minute, pause the video, work through part B in the note guide, and check your answer before we move on to the rest of the lesson. Next type of transformation we're going to talk about is called a reflection. I'm going to say a reflection is a transformation where the figure is flipped to the other side of a line of reflection. So if I have my original triangle ABC and then a line of reflection R, what's going to happen is I'm going to take ABC and reflect it over R, where any points that started on the line of reflection stay where they're at. And all the other points are going to move an equal distance to the other side of the line of reflection at a right angle. Okay, so we can think about making mirror images of figures here with our lines of reflection, across our lines of reflection. So let's get into graphing reflections. Problem 3, part A says, what's the image of triangle ABC reflected across the y-axis? So the y-axis is my line of reflection. And to describe a reflection, all you need is that line of reflection. Remember, our y-axis is the vertical axis. Okay, probably biggest mistake I'm going to see from students on reflections is just getting that line of reflection in the wrong spot. So we'll kind of point that out as we go. Meaning that if I want to reflect across that, I'll take each of my points, where we have A, and figure out how far it is away from that line of reflection. It is 1, 2, 3 units from the line of reflection. So I'm just going to go 1, 2, 3 units in the other direction. We'll say that's my A prime. Okay, so that's the idea of taking A and reflecting it across a line of reflection. Now again, the way that's going to work is if I make a line from A to the line of reflection, it's going to be as congruent to the line from the line of reflection to my A prime, to my image. And then also that line between those 2 points is going to be at a right angle to the line of reflection. Alright, next up we can do B. Now B's already on the line of reflection, so we're just going to leave B prime at the same spot as B. And then other kind of way we can think about this is if I take my coordinate, so right now C is at 4, 2, and think about what's going to happen kind of more numerically to that coordinate if I reflect to the other side of the y-axis. Well, the y values are going to stay the same. The x values, however, are going to switch signs. So without doing any counting, I know based on the numbers here, c is going to go from 4, 2 to c prime at negative 4, 2. It's kind of two different ways to think about that reflection, more visually, okay, or we can think about it numerically. All right, connect my dots. There's my reflected image. Now, once again, these triangles should be congruent to each other. We shouldn't have distorted the size or shape. Okay, so they are in a different orientation. They're facing different directions. Okay, but if you're reflecting an image, it should still be congruent to the pre-image. All right, part B is the same idea. Why don't you take a minute, pause the video, work through that, and remember to check your answer before we move on. Next thing we're going to look at are making some reflections happen across just some more difficult lines. So let's take a look. Problem 4, part A says, what's the image of P at 3, 4 reflected across the line y equals 1? Okay, so y equals 1 is our line of reflection. To graph that, I'm going to find my y-axis, which once again is my vertical axis. I'm going to find 1 along the y-axis, and then I'm going to draw a horizontal line through that 1, okay, intersecting the y-axis at 1. Okay, and this line represents all the coordinates that have a y value 1. Okay, now that trips students up sometimes just because the y-axis is the vertical axis, but y equals equations will be horizontal lines. And then to make that reflection happen, we'll figure out how far P, our pre-image, is from the line of reflection. It's 1, 2, 3 units away. So we'll just go 1, 2, 3 units in the other direction. Okay, there's my P prime. There's my reflected image. Okay, part B is the same idea. Why don't you take a minute, pause the video, work through that, and make sure you check your answer before we move on. In problem 5, we're going to look at finding a line of reflection. Now, just like we want to be able to write translation rules, we also want to be able to write reflection rules. And really all there is to a reflection rule is figuring out what that line of reflection is. So let's go ahead and do that. We'll do a couple of these together. Problem 5 says, name the line of reflection that maps each point to its given image. So for part A, if I want to reflect from point A to point F, okay, A to F here, what I need to do is I need to figure out what's directly between them. What is my line of reflection between them? Okay, well, A is 4 units away from F, so the middle of that is going to be right here. Okay, meaning my line of reflection would just be my x-axis. So I can write that line of reflection as just the x-axis. All right, or I suppose I could say y equals 0. Okay, either one of those would work to describe this horizontal line of reflection. Okay, part B, same idea. We want to reflect from C to B. Okay, C to B here. Once again, we want to figure out what's directly in the middle of those two. Well, here's the midpoint between C and B. So if I draw that line in, we'll have a vertical line which intersects the x-axis at -1. So I can describe that line as x equals -1. Okay, so there's two examples of coming up with the line of reflection, or in other words, the reflection rule for reflection transformations. The last type of transformation we're going to talk about is something called a dilation. I'm going to say a dilation is a transformation in which a figure is either enlarged or reduced by a scale factor n around a center of dilation C. Okay, so we have our center of dilation C. We'll pick a scale factor and then essentially either blow that figure up or shrink it down, all right, around that center by that scale factor. Okay, we'll show you how kind of that scale factor and center relate to each other in a second here. Last thing we'll say is just that a dilation is an enlargement if the scale factor is greater than 1, and it's a reduction if the scale factor is between 0 and 1. So first thing we're going to look at doing is describing dilations, okay, by their scale factor. So problem 6 says determine whether each dilation is an enlargement or a reduction and find its scale factor. Okay, so in this one, in part A, we want to go from ABC to triangle A prime, B prime, C prime. So in other words, our solid figure to our dash figure. Now first off, is that an enlargement or a reduction? Well, it shrunk from the solid to dash, so I'll say that's a reduction. And as far as the scale factor goes, the way we'll calculate that is I'm going to say that the scale is equal to the length of the image, all right, over the pre-image. Okay, so scale is image over pre-image. So in other words, what I can do is I can just find a length that's countable on the image, such as this vertical right side. It has a length of 1, 2, 3, 4. Divide that by its corresponding pre-image length. Okay, on the right side it is 1, 2, 3, 4, 5, 6, 7, 8. All right, 4 over 8 is going to reduce down to 1/2. So I know my scale factor for this guy here is just 1/2. Okay, it got half the size as we reduced it down. Now, like we said, we will have an enlargement if this scale factor is greater than 1, reduction if it's less than 1. Okay, so how you describe it and the scale factor you come up with should probably match as far as that goes. All right, that's part A. Why don't you take a minute, pause the video, work through part B, and then check your answer before you move on. Next thing we're going to do is actually make some dilations happen. Problem 7, part A says, what are the images of the vertices of triangle ABC for a dilation with center 0, 0 and scale factor 1/2? Okay, graph the image of triangle ABC. So our scale factor is 1/2 again. And the way this is going to work is we're going to take each point. So let's say right now A is at 1, 4. And we'll dilate it to A prime, which will be at 1, its x-coordinate, times the scale factor. And then also its y-coordinate 4 times the scale factor as well. Okay, so to make a dilation happen, take each of your x and y coordinates, oops, that should be an A prime there, and multiply them by the scale factor. So we'll have A prime then at 1 times 1/2 is just 1/2. 4 times 1/2, half of 4 is a 2. So my A prime then is going to be at a 1/2, 2. That'll be the A prime. Okay, notice A and A prime fall on the same line. Essentially right now A prime is half as far away from the center dilation, the origin, as A is. And we can do the same thing with the rest of our points. B, our pre-image, is at 2, -2. It's going to turn into B prime. At half of 2 just be a 1. Half of -2 would be a -1. And same idea with C. C is currently at -2, -2. And that'll turn into a -1, -1 when I multiply both those 2's by a half. All right, so there's my dilation image. Okay, different size, obviously, but same shape. These will be similar figures. Okay, if we get something that looks completely different, we know we did that dilation wrong. All right, part B is the same idea. Once again, take a minute, pause the video, work through part B, and then check your answer before we move on. Last thing we're going to do this lesson is look at a couple of applied dilation problems. Now, these will be similar to some problems we looked at in the similarity chapter. Okay, just taking a slightly different perspective on them, looking at them through the lens of dilations. All right, so problem 8, part A says, a magnifying glass shows you an image of an object that is 7 times the object's actual size. The photo shows an apple seed under this magnifying glass. What's the actual length of the seed? Okay, so we have the actual apple seed. We are enlarging it, we're dilating it, we're blowing it up to what we see in the magnifying glass here. Okay, we know the scale factor, we want to figure out how big the actual seed is. Okay, it'd be difficult to measure the actual seed, it's going to be easier to measure it under the magnifying glass. All right, to do that, we're going to use that same scale equals image over pre-image formula. And I'm going to fill that in with the information from the question here. Okay, first off, it says it shows the image, an image of the object 7 times the actual size. That means that 7 times is my scale factor. So we can say 7 equals. And then the photo shows an apple seed under the magnifying glass. Okay, in the magnifying glass, I'm going to say that's our image. Okay, that's the seed after it's been blown up. So for the image, I'm going to fill in a 1.75. And then what I'm looking for in this one, when I want to know the actual length, that's my pre-image. We'll call that the X. Okay, anytime you see actual in a story problem like this, that should tip you off that you're talking about the pre-image. Okay, so I have a simple equation here I can solve. Kind of like solving a trig equation. We'll multiply both sides of the equation by x to cancel out the fraction here. So in other words, I have a 7x is equal to 1.75. And then divide both sides of the equation by 7 to give us our x equals 0.25. All right, so we'll say that actual seed length is just 0.25 inches. All right, so there's an example of a applied dilation problem. Fill in this scale factor equation, and then you have a simple equation to solve. Okay, that's it for this video. Shut this down. Now, there is a part B in the note guide as well. So take a minute, make sure you work through that, make sure you get your answer checked. Okay, make sure you're doing things correctly before you move on to the Math Excel practice.